So I hate to disappoint everyone. The title of this talk is Speed Science. We will not actually be talking about methamphetamine production or any science behind it. So instead we're going to be talking a lot about goals. Sorry about that. We're going to be talking about a lot about goals, and today we're going to be talking. Our main goal is going to be going fast, getting faster, and achieving more. So one of the things that I like to think about whenever I'm dealing with any kind of a performance problem is that slowness is a bug. This is really comforting for me because mostly in my application I deal with bugs every day, every hour, every minute, a lot. And the great thing about bugs that I really love is if you have a bug, you can reproduce it, and if you can reproduce it, then you can squash it. So a little bit of audience participation here. Does anybody know what this shape is? Okay, so I heard triangle. Any other? Isosceles triangle. That's very specific. So I hate to tell you, but this is actually a square. This is known as a speed square. It's used in woodworking. It's used for making fast angles. Here you can see it making fast angles and square edges. So from now on, for the rest of this talk, this will be a square. You've been informed. So programming has our own speed square. It's slightly different, and it looks kind of like this. We've got I/O, CPU, and RAM, and these are all resources that we can trade for speed. Similarly, we can trade one resource for another if we're overbooked on one. So, okay, how do we make things fast in general? Well, first we're going to find a bottleneck. On a side note, I highly recommend, if you don't have an industrial engineering background, or even if you do, to check out this book called Goal by this person who I can't pronounce their name. So just Google the Goal and book, and then that's all I'm going to say about that. Once we found the bottleneck, or even to find the bottleneck, we can use the scientific method. It's going to look a little bit something like this. We're going to touch on it later. So, I kind of started off relatively quickly. For those of you who don't know me, my name is Schneeman, or Schneems. I really love Ruby. And as Pee Wee Herman once famously said, if you love something, why don't you marry it? And so I'd like to introduce you to my wife, Ruby. She is actually a pipeline programmer. It's like a house divided. And we're actually really excited to announce that we're having a child. So baby's coming in June. We've been talking a lot about names. Is it going to be a boy? Is it going to be a girl? And I was like, all right, if it's a girl, we have to name her Pearl. She's like, what about a boy? I'm like, I don't know, Haskell? And then we were like, well, no matter what, the middle name should be something we could both agree on, and we decided on pseudo, and we'd be like, pseudo clean your room. Pseudo clean the dog. So I worked for Heroku on the Ruby build pack, among some other things. And I'm not going to have time for questions at the end of this, but we will have a booth that's going to be open up tomorrow. Please come by the booth. I will be there a lot. Also, Koichi Sasada has a talk tomorrow. Please go to that. It's going to be really good. Also, Terrence Lee has a talk, so please check this out. Also, I'll be doing a book signing. If you come, I wrote a Heroku book, and I'll be giving out free copies. If you come by the booth, you can get some more information. So. I also have Rails commitment, and I run a really small conference down in Austin called Ruby Weird. All by myself, and not with Caleb Thompson sitting in the front row wearing a Ruby Weird shirt right there. Okay, so I'd like to start out with a story, if I may. Once upon a time, there was an application, and I was working on this application. It had some requirements, it did some things. It downloaded a really large zip file. It then decompressed the file, and we did some work on that file. And that was pretty much it. That's the gist. That's really all you need to know. Was this thing fast? Does it sound fast? It does not sound fast. taking a look at our speed square, we can kind of look at those individual things and say, okay, what resources are we using? It's like, okay, we're using I/O, we're using I/O and CPU, we're also using RAM and CPU for the processing. So first of all, I had a hypothesis, and I was like, okay, this thing isn't fast, let's use some more CPU. Heroku has this really nice thing, this really neat feature that we launched, I have no idea when, but relatively recently, called the PX Dyno. It's got 6 gigabytes of RAM, and one PX Dyno is actually an entire AWS instance, which is pretty cool. And the benefit of this is you get a lot, there's no sharing on it. We're not going to subdivide up that AWS instance into other smaller containers, so you get less noisy neighbors. Once we have this, I've now got a bunch more resources at my disposal, but now I need to take advantage of them. To do that, we can use more threads, and more threads is going to be more CPU load. Has anybody ever used Sidekick? Okay, cool. There's going to be a bunch of rhetorical questions. A lot of hand raising. Get that blood flowing. Okay, cool. Well, great. So you're familiar with Sidekick background workers. The first thing I did with this, I was like, oh, I have this huge box. I'm going to set Sidekick concurrency to like something huge, like 30. And at the same time, we're going to be downloading, unzipping, and processing with 30 threads, kind of all at the same time. And when we did this, well, so it was definitely faster than just sequentially doing it, but it was still pretty slow. And I was like, man, you know, why is that? So my next theory was that we still had unused CPU. I was looking at some metrics, and like CPU, we still had plenty of it. And I was like, okay, great. Let's change this from 30 up to 60. And does anybody know what happened? Okay, well, yeah, it got slower. When this happened, I was like, come on, like, you gotta be kidding me. So it turns out that we weren't CPU bound, so we can strike that off. We go back to our little diagram and say, oh, what else do we have a lot of? What else are we doing a lot of? And it turns out that we have a lot of I/O in this process. So there are different types of I/O. On the first one, we have network I/O, so we're actually downloading the file. We're using the network adapter. On the second one, we're only using the disk. So my first theory was like, hey, networks are inherently slow, so that's got to be the problem. To test this out, I tried a bunch of different solutions. I tried a bunch of different libraries, curl, curve, shelling out, Typhoeus, and then I came to try the thing that all Rubyists advocate when they're talking about making things fast. I heard caching, not quite. Really, what everybody advocates is using Go. That is the way to make Ruby faster, according to 90% of people on Twitter. By the way, 70% of statistics in this talk are going to be made up on the spot, including this one. Okay, so one of my coworkers has a really great utility called htcat, and this is written in Go, and it will parallelly download and stream large GIF requests. It's really cool. There are other libraries like it, but one of the neat things about this one is it will actually start piping. It will start streaming to the pipe, similar like if you were going to cat a file, you can pipe that to something else, and it will start doing that immediately as soon as it can. Unfortunately for us, and maybe for a lot of people on Twitter, Go is not the answer, and network I/O is not the problem. So that kind of leaves us with really one thing, and that's disk I/O. In this case, it was pretty simple to test that out. So I had Sidekick concurrency of 30, and I changed that to 4. And then everything was like screaming fast, like really fast. Previously, like we were not able to keep up with the queue, and then all of a sudden it's like we've got spare cycles. And what actually happened was our hard drive, the disk, was at max read-write capacity. We were downloading that file and putting it onto the disk, then we were unzipping it and basically copying from one area to the disk to an even larger area of the disk. And we had all of these threads just kind of sitting there idle. It's as if you have a dinner party of 30 and you only have 4 forks, and everybody's just grabbing that fork and trying to eat as fast as they can. but nobody can get anything done because there's a limiting resource. So in the end, we actually ended up using 2x dynodes, and the moral of this story is that you can blindly try things all you want, but it's not very scientific. It will work eventually, but maybe there's a little bit of a better way. So going back, I had a slide of the scientific method, and we can take a look and see, here's the things that we kind of did. You've heard me use the words theory and hypothesis. Then I tried something, and then we observed from that, and then kind of repeated the whole thing over and over and over again until we got the results that we wanted. Notice that we are sort of missing out on this one, on this research one, which is pretty critical. So one thing that is very, very important in all of science is that it's repeatable. Does anybody know who these two people are? Fleischmann and Pons. Wow, that's great. I was not expecting anybody to get that. Okay, so this is Fleischmann and Pons, and this is not cold fusion. So cold fusion is the idea that, so fusion is the thing that powers the sun, and the idea of cold fusion is that you could have that at temperatures less than the sun, which would be great, and it would provide lots of energy. And these people claimed and actually published and said, hey, we've done it. And unfortunately, it wasn't repeatable, and lots and lots of people tried it. And it is good in the sense that it's kind of showed that this whole peer review thing can work, and it does work. But they are unfortunately the poster children of making these kind of hyperbolic scientific claims without actually using science. So they did not use good science. We, on the other hand, are going to use great science, the best science. We're gonna measure and benchmark. So Heroku did add some metrics. This is an older view of what our dashboard looks like. We explicitly call out speed, throughput, and then CPU and RAM. And the interesting thing for me is you can actually correlate and be like, oh, hey, CPU use shot up here, and then like throughput, took a nosedive or not. And this won't tell you why you're slow or what exactly is going on, but it will give you a high-level metric that you can use to then ask the question and get a low-level metric. So that's kind of our basic research. Again, we want to reproduce the slow. So RAM is the one thing that we haven't really touched on. Ruby is typically going to be RAM-bounded. And this is because Ruby is a managed language. So some of you might already know this, just bear with me for a little bit, but this is crucial to understanding the rest of my talk. So Ruby uses a garbage collector. And if you have questions about the garbage collector, Koichi Sasada is currently here. He's great. Haruku Ayrton and Nobu and Mats to work on MRI full-time, which is pretty cool. So the garbage collector is going to allow us to do things like just say, here's a string literal, I want a string, without having to say, all right, we're gonna allocate 5 bytes for this string. A lot of people aren't really intimately familiar with different ways that Ruby can consume more memory. So one of the most obvious and what people think of when they think of memory use in Ruby is retained objects. So here we've got a loop, and we're just looping around. We've got this constant. Constants are never garbage collected; they're global. You can't collect something that's global. And we're just adding a bunch of strings to it. And when we do this, and we take a look at the process memory, it's 7.32 gigabytes, which is kind of a lot. It's kind of large. I mean, I guess it is 100. Is that 100 million? Yeah, that's 100 million strings. So why is it so large? So Ruby allocates chunks of memory, and then in those chunks of memory, it has slots where it can put objects. So as we are going through and we're looping, it is going to put 1, 2, 3, 4, 5, 6, 7 into different slots. It needs one slot for each of those. Whenever we're out of slots, we need to allocate more slots. So then now we have twice the memory. You can think of this. I've chosen the bus analogy in kind of a shipping container, really anything you can put things in. And so now we can actually go all the way up to 14, but we have to go up to 100 million. So we just keep on allocating more and more and more until we get enough. So this, to me anyway, makes a lot of sense where we say, okay, Ruby's using a large amount of memory, and here's where it's coming from. We need this. It's a retained object. So the second way, which is a lot less intuitive, at least to me, is allocated objects. Here we're doing the exact same thing, except for instead of storing it as an array, we're just going to output the string. We use it and throw it away. This is only going to take up 21 megabytes, which makes sense. We're not actually doing anything. We fill up our bus. We are going to run garbage collection, and our garbage collector is going to say like, hey, it doesn't look like you actually need any of these objects. 1, 2, 3, 4, 5, 6, 7. Guess what? You're not going to use it again. So we can get rid of it, and we can put another object there. And this is a very oversimplified version of garbage collection, but it will help us. It will help us later. So it looks like garbage collection is going to save us from everything forever, and it's like the perfect answer to all things. If that was true, I wouldn't be up here. So here's another example that is kind of it's an in-between. So what we're going to be doing is we're going to be looping through a million elements again. We're going to be adding them to an array. The interesting thing is we're going to not return that array. We're not going to do anything with it. So it's not a constant, nothing has a reference to it. And then we can call garbage collection on it. We can force a garbage collection. So what happens when you run this? Well, your application is still going to use 7.32 gigabytes of RAM. Which is kind of surprising, right? It's like, well, the garbage collector could just get rid of all that stuff. It just throws it away. Well, to understand why, you can, or to verify this and prove this, you can take a look at GCStat, and we can look at total freed objects. And we can verify and say, okay, the garbage collector is doing its job. It did free 100 million objects here. So why is it still so large? Why is our memory use so large? So we can't clear a slot while a reference to that item still exists. So what's happening is we fill up our buses, and after we've done this, we've gotten to 14, and we need to keep going. We're going to run garbage collection, and after the entire program has finished executing, yes, we can clear those slots, but Ruby never actually releases memory. Ruby only memory usage ever goes up. We basically assume that once we've allocated memory, we're going to need that for the future. Also, freeing memory to the operating system is an expensive operation. So even though we don't need those things anymore, we still are going to hold on to that memory. So it's important, not necessarily that it's retained forever, but just that it's retained for a while. So that array actually needed reference to all of those things. And while the array was in memory, we couldn't clear them. So I do highly, highly recommend that you test everything. Even these slides, like as I was writing these, I realized I was like double checking everything and realized there's a giant mistake in them. So please, just if you're interested in getting started with performance stuff, like double check me, verify that what I've said, like that's good science, peer review. So the experiment is super, super critical in benchmarking performance. Like never go in and be like, I think I know why something is slow. Please always double check. So okay, back to speed. How does this actually affect your Rails app? So you can kind of think of your Rails app as a collection of retained memory. These are going to be things that live forever, or forever in like a Ruby world, such as like a database connection or your high-level Rails app, your controllers, any constants, any code that you've loaded. So that's going to have a base set of memory. And on top of that, it may be larger, maybe smaller. We're going to kind of spike up and down, sort of like a level on a soundboard, this allocated memory. And our total memory usage is going to be the combination of both of those. So why this really affects you, it helps if we take a look at something like, let's say we've got a bunch of memory, and we're in a Rails app, and a request starts. So we're processing, we're hitting the database, we're processing, we're loading up templates, and we're processing and doing some other stuff, turbo sprockets 3, we're processing, and so we're creating these objects, and while this request is still going, we still need them, so we can't clear them. So now we're out of memory, all of our slots are full, what do we do? Okay, well Ruby can run the garbage collection, but it looks like we need a reference to all of these objects. So we can allocate memory. So we add an extra bus onto our memory, and then finally we're done. We're done with the request, we can deliver the response, and we no longer need a lot of those objects. Granted, this is definitely an oversimplification, but it helps. Eventually, we can go back and we can say, all right, we're going to run garbage collection, and we don't need those objects. We can just mark them, or we can just get rid of them. And we get rid of them. But you notice that our bus count is still high. So Ruby is going to increase memory use without retention. Even if you're not constantly retaining objects, even if that retention number stays the same, if you have one request that loads up, millions and millions and millions of objects, and only one person ever gets that request once in a day, guess what? Your app is going to be pegged at that memory usage, and charged that memory usage by the operating system until that process dies. So object creation takes up RAM and it takes up time. I do also recommend checking out generational GC. Don't have time to cover right here. So, okay, that was all relatively critical for a customer story that I have. One day, a ticket came into Heroku, and I mentioned I work on the Heroku Ruby build pack. It's this open source thing. Whenever you run git push Heroku master and all that stuff flies by the screen, that's actually me sitting at a computer, like furiously typing. So if anybody tries it right now, it won't work. Sorry. That's not entirely true. Terrence helps out quite a bit. So one of the things that we do is make recommendations. And we say, use this web server or do this other thing. And in order to do that, we have to provide configuration. And some of the things that we care about are some of the things that our customers care about, which makes sense. And so one day, a ticket came in, it hit regular support, and the customer said, my app is slow. And the supporter looked at it and they're like, well, I don't know, maybe it looks like a Ruby thing, like we'll escalate it up there. And so I get to look at escalated tickets. And they said the app is slow. I checked metrics. It looks something kind of like this. And you can see that the RAM they were using is just like way too high. So they're using swap. That's this red bar. And that's actually indicating that we've used up all of the available RAM. And we're starting to use the disk, which is really, really slow, like really, really, really slow. So this is what I was thinking is actually making their application slow. The next question, of course, is going to be why. And obviously, I asked the customer, and if you've ever worked in support, you've got answers like this. It didn't used to happen, and we didn't change anything. It's totally you. And then I'm like, we haven't deployed anything in like a month, so. Whenever these types of tickets happen in Heroku, a lot of times what people don't realize is that their gem file or their gem file block changed. One of their devs ran bundle update something, and a minor version or major version had some bugs in it, and they didn't realize that was an issue or even think to look into it. So my number one hypothesis was that RAM was increasing due to misbehaving code in a gem somewhere. We don't know. In order to test this out, I wanted to be able to boot the app, hit it with requests, and profile the memory. In order to do this, I wrote up something called derail benchmarks. It allows you to actually do those things without having to run your server somewhere. You can do those in a single process. And it uses RapMock, and then we can do really neat things like wrap it in other tools like StackProp and Memory Profiler. So derail benchmarks is going to boot the app, it's going to process the request, and then, conveniently enough, we're going to use Memory Profiler by Sam Saffron, who's at this conference. Please go give him a high five and be like, your memory work is awesome. Also Koichi Sasada has another gem called Allocation Tracer, which helps as well. So in derail benchmarks, you can run reproducible, and I have an application called codetriage.com. It helps people get started with open source. It sends you one GitHub issue per day. And this is just something I run so that I can have something in production on the platform that I care about, and I get a real customer experience. So for those of you who weren't paying attention, that was codetriage.com. 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 Sign up today. Okay. And so when I ran this, I got something that looked like this. On every single request, here's all of the object counts of what we're using. And rack, okay, yeah, using a bunch of rack, using action pack, that makes sense. Active support, it's like, whoa, Hashi. Where did Hashi come from? If you know me, you know I have certain feelings about Hashi, certain blog posts about Hashi. And it was really remarkable to me that Hashi is using, everybody gives active support a hard time. It's like more objects than active support. So Hashi is incredibly expensive. And in our case, it was using lots of unneeded objects. And I said, okay, I didn't put Hashi in my project, I'm not using it. I look at my gem file.lock, and apparently it turns out that Omniauth uses Hashi, which actually makes sense. The same author of Hashi is the same author of Omniauth. It's like, oh, they use the same tooling. Originally, I wanted to remove Hashi from Omniauth, and the author of Omniauth was like, that might be a little heavy-handed. So I basically found some hotspots where and this is, and we were not authing. This is every single request. Do any action in your entire application. Yeah. So I fixed it by just memoizing a couple items, and instead of having to recreate the objects, we just use the same one. So basically, we are using up more memory by retaining that, but ultimately creating less objects, which is less memory, confusingly enough. So I did this, and the application limit of our send it over, the customer tried it out. The application is still over the RAM limit. So okay, hypothesis number 2. We're still restricted to the gem file. Maybe it's something else. Maybe it's a bad gem using too much RAM at require time. Okay, in order to do that, how can we test it out? I had the customer send me the gem file and the gem file.lock. And I was thinking, well, hey, how can we figure out which of these gems is, it's just like, if the gem just loads and retains a ton of code, how can we know about that? Maybe it's not something on every request. At the time, there was no tooling for benchmarking required memory use, and so, let's write one. All right. The general concept is pretty simple. We're going to measure RAM before and after require is called, and we're going to be using a library called getProcessMemory. And now, one thing to note if you're like a super memory geek is that it uses RSS. RSS stands for resident set size, and this is not memory. This does not take into account shared memory use. It is a close-ish approximation of memory, but and for our cases, it's probably good enough. But yeah, it doesn't take into account shared memory. The next thing we're going to do is we're going to monkey patch kernel.require because we can, and it's awesome. Yeah, monkey patch because you can. Okay, and then we're going to run it, and we're going to get an output like this. It's going to spit out every single file and the associated cost. So here it looks like will paginate active record costs 1.49 megabytes, which is a little large, but I don't think that's where our big problem is. Now that we know where all of our memory is, we can sort this, and it looks like mail is using about 40 megabytes of memory, which is slightly larger than will paginate's 1.5. When we count it all up, this one gem accounted for 65% of all of the RAM at boot time. And we haven't even done any work. We haven't hit 1,000 requests or anything. Remember in that slide I had where the retained on the bottom, this is the starting memory that you have to deal with. And anything you allocate after that is just going to go up. So in order to debug further, we're going to have to dig deeper. Whenever you require one gem, it requires other files. And we need to see where exactly inside of mail is causing that problem. So we're going to use a tree in order to do that. Each node can have many children. Each child has a cost. It's going to end up looking kind of something like this, where mail will load one layer, and that will load the next layer, and that will load the next layer. We have a tree class that we're going to store these things in, and then when we're done, we can sort the children and print them recursively, something that looks kind of like this. The final process looks like this. We're going to instantiate a new tree node, and this might be mail. So we've already required the application, and now we're going to be requiring the mail gem. We are using a stack in order to keep track of where we are. So the last thing in the stack would be the application, and that is going to be the parent. And we're going to push the child node, which is mail, onto the parent. So we're saying that mail belongs to the application. Finally, we're going to add the mail gem and say, okay, now we're going to require everything inside of the mail gem, so we need to push that onto the stack. We take a measurement before, we call require, and this is actually what goes down, and then this thing will get called again and again and again and again and again until all of mail has been fully required. When it's done, we pop the last thing off of the stack, which at this point in time will be mail because everything else has been popped off the stack, and we take a memory measurement again. Finally, we record the cost and store that. So one thing, if you're interested in doing this yourself, it is really important to note the ensure block. One thing I didn't realize, well, I realized but didn't fully sink in, was that a lot of people actually require files that don't exist. They expect that to raise back a load error. And if we're not ensuring that we're popping something off the stack and recording the memory, then in the event that we try to require something that is bad, then this code just won't run. It'll be bad. Okay, the final result of all of this looks something like this, where we have, we can see sort of the tree structure, we see application requires mail, require mail parsers, and we see, oh, it looks like mail parsers takes up 20 megabytes nearly, 19.24 megabytes. I open up an issue, I raised awareness. One thing I'd like to point out is you don't necessarily always have to fix a bottleneck or a performance bug whenever you find one. Even just pointing out, hey, there is one, raising visibility sometimes can be just as important, or is just as important. And I didn't fix this, but somebody else did in Mikkel Mail number 817. And basically, they just said, so if you're not familiar, inside of mail, there's a parser that actually parses mail. Whenever you reply back to GitHub and you say, hey, this issue looks great, and that gets parsed by probably Ruby code, and they pull out what you said and drop the rest of the text, drop the subject and all that other stuff, and will actually generate a new comment. So some applications do actually need a parser in there. And Mail switched over from using the treetop parser to a Rail parser, which is much more efficient, much faster, but it uses the trade-off of more memory at boot time. So if most applications don't use this, which is why, and our customer wasn't using this, most applications are not parsing mail, so they don't even need it. So the fix was actually to just lazy load that, or if somebody really wants to load it and take advantage of copy and write optimizations, then they can require it before your application works. So okay, what happened after we did this? Well, the customer's RAM usage dropped dramatically. It was no longer swapping, and instead of just kind of crawling along, they were now fast. They're like screaming fast. And they're like giving me high fives over the internet, and they're like, great job, and I was feeling really good about myself. And you don't have to care about that, it's okay. I work remotely, so I work at home alone, so that was really like me giving myself high fives at my desk, my standing desk. Some of the takeaways is like we want to remember to reproduce the slowness bug. These are bugs. They're problems. In this case, it was fixed with code, or can be fixed with a different version sometimes. We want to definitely make sure to get visibility with benchmarks and and use these methods and use this this process of repeatedly asking questions, digging deeper, and gathering more and more metrics. So, kind of real quick, has anybody here ever made a bad code deploy on a Friday? Okay, so this will happen, and then you'll like, oh, I'm going to deploy a hotfix, and you're like, oh, I totally fixed it, and it's like, whoa, and then like your weekend is just like gone, and your coworkers' weekend is just gone. And if you have a support, then they're just like, oh, and everybody's like, why did Schneeman deploy that? So this happens to everyone. Like, whether you raised your hand or not, like, it's kind of an eventuality that it will happen. So I have a modest proposal. Don't deploy on Fridays. Now, instead we can go shopping or ride roller coasters or something. Okay, so that's not going to fly. Instead of just not doing any work, I'm proposing something I'm calling Fun Day Friday. If your application is slow, maybe instead of complaining about it and just being like, oh, why is this thing so slow? You could look into it on Fun Day Friday. You can run some benchmarks. You can maybe implement some of this. You can take a look at the slides. If you're constantly complaining you can't find files, you can't find methods, and the code base is a mess, it's like Fun Day Friday. Or if you are like constantly having to stop it's like your boss is like, oh, this feature has to be delivered tomorrow, and they come over to your desk and you have like 1,000 files open and like 10 branches checked out, and they're just like, what are you doing? And you're like, oh, I couldn't stand it anymore, I just had to refactor right now. Instead of doing that, Fun Day Friday. A lot of times I hear companies wish more companies sponsored open source, and guess what? Your company just sponsored you to work on open source on Fun Day Friday. If you're not sold, it's okay. This is actually not just something I'm randomly recommending. It will give you more accurate deadlines. It's a well-proven technique. It's called time boxing. It will hopefully lead to less burnout. And if your boss is ever like, man, I really want to hire more senior developers. Like, I don't know of a boss who doesn't say that these days. And you can be like, oh, you mean like developers that make refactorings and speed improvements and contribute to open source and know the libraries really, really well? It's like, maybe you can have us do Fun Day Friday and learn all of those things instead. So it's not just as simple as doing this. Unfortunately, it never is. I hate to tell you, but if you're going to participate in Fun Day Friday, you have to report on your progress to your team. You have to let other people know you're doing this. Report it to your team, report it to your boss. You're going to be amazed. So I actually kind of started doing this without really telling anybody. And then just after the fact, I would be like, hey, I made this patch to Rack or to Rails, or like, look at this thing. And then now, like, whenever somebody at the company is like, hey, I've got a question in Rails, like, they come to me. My boss is like, hey, there's this critical like thing that's failing for our customers. Why don't you like, take a look at that? And I'm like, wow, this is amazing. It's like no longer, it's not even Fun Day Friday. It's like Fun Day Tuesday. And I get to work on open source. I am like the luckiest guy in the world. So in addition to reporting your boss, please report to Twitter, #FunDayFriday. There are a lot of other people just also randomly tweeting Fun Day Friday, so it's okay. If you mention me, then I'll like retweet it, and hopefully if you see somebody doing this, like give them love and be like, even if they're like, hey, I spent 8 hours like looking at benchmarks and like got nowhere, it's like that's progress. Or they're like, or maybe they're like, I signed up for codetriage.com. That is awesome. So please, please give love, give love. I know we're a little excited. We've had a lot of fun today. Thank you very much for coming. I want to leave off with two relatively serious questions. And this is a silent meditation. You don't scream out any answers or raise your hands or anything. So, thank you very much.